So last day we talked about the core idea of backpropagation, and then the day before that we talked about what deep learning in neural networks is all about. But today we will be talking about how to train neural networks. So we have seen that neural networks are extremely powerful function approximators, and we have seen how to learn the parameters of that function, of the unknown function, via backpropagation. But all that I have mentioned in the mathematical structure, that is already coded, hard coded. You can use libraries to code that. So the goal of today and tomorrow is to understand, first of all, the process, the entire process that you can see on the screen. And also, why do we do like that? Why do we divide into train and test? What is validation? Why do we divide into batches? And all other deep learning techniques, which is very important. Okay. Today we will learn the theoretical understanding of that, and tomorrow we will be hard coded live using PyTorch. And today I will talk about mostly about the pseudocode structure, how the entire thing happens. Okay, so let's get started. So this is a learning process of deep learning. So let's understand what do we have initially. Let's start from the very beginning. So we have the data points xi and yi. This can be any dimension, and your goal is to find the function such that y hat is very close to y. So we define it like loss of y hat comma y is very low, where y hat is nothing but some function of xi and theta. So we minimize the loss L y hat I, rather summation of L y hat I. Loss is equal to 1 by n summation of I from 1 to n, loss of L y hat of I, to get optimum theta. So this is a basic structure. This is a theory. So this is a fundamental theory of what we are learning. But let's consider the practical side of it. Like what will happen. So let's take a very simple example. So when we do it, what happens? So let's take an example of this. Simple example. Where we have this, let's say, these points. Like this. Okay. Now, there are multiple things you can do. So you can assume that, so let's take 3 examples. So this is x and this is y. Okay. So let's take fx to be some wx plus b. Let's take fx to be some w1x, sorry, some w2x square plus w1x plus b. And let's take 3 to be some f of 100 x to the power, or f of 10 x to the power 10 plus f of, sorry, w of 9 x to the power 9 plus dot. So it's a x to the power 1 plus b. So it's a 10-degree polynomial. It's a 1 degree. It's a 2 degree. And this is a 10 degree. Okay, so it's a 10-degree polynomial. And let's see how it will fit. So if you fit it, so let's give it different colors. So let's try to fit it. So if you fit the number one, we will get something like this. Okay. Hi everyone, can you mute yourself? If you plot, so let's say this is the best line. If you optimize the theta, you will get. after optimization. Best. So right here W and B are theta, right? Best line. If you take the blue, you will get something like this. And if you take the green, you will get something like this. Okay, 10-degree polynomial. Now the question is that which is a good functional fit? What do you think, guys? This one? Yes, Vivan, tell me. This one.
So I think the blue one, because the red one does not produce a very accurate representation, and the green one is very susceptible to anomalies. And but the blue one is kind of a more general functional.
Very good. All of you agree with Vivan? Yes, Arav?
Yeah, I was also gonna say because the other one is too like it's too biased, and then the other one has too much variance. So the blue one is a good fit in the middle.
Very good. So this one is a very good fit. So as you have said that this is susceptible to anomalies and this is too biased. Like this doesn't fit it well. Doesn't fit it well. So what to do? So therefore, this is the qualitative way. But when we have a large neural network, the question is that when we have a large neural network, what to do? When you have a large neural network, that's the main question. What should one do? So that's we are going to learn here today as one of the most important topic. So as you said, this is optimal in some sense. Now the thing is that this is not taken care of the training because for different functional assumption, different things come up, right? But neural network is a huge function on the process. So the thing is that as you train the neural network, as you train it, you will see that it goes from this too biased to optimal to high variance, like variable. So we call it high bias. Okay. So this leads us to the idea of something called bias variance trade-off. So what is a bias variance trade-off, guys? So bias variance trade-off is nothing but we have to understand that we have to actually measure. Yes, Saurav?
Didn't we learn that the ways to fix this was either standardization or normalization?
Sorry, can you come again?
Didn't we learn that I think from the old professor that the two ways to fix this were standardization and normalization?
Uh, I mean, what one idea can be? I mean, that is that question is varied from like if for a simple model, yes. But what I'm telling you is this is a bigger general theory. So what
Yeah.
the other person may have said is for that specific case,
Okay.
probably. But this is a general theory that
Yeah.
applies everywhere. Okay.
Okay.
So to do that, we have to measure the bias, measure the model performance or bias. So let me pull up a picture that is usually used everywhere for the model, for the bias variance trade-off. Uh, so this is one picture and this is another picture. So what do these pictures say? So this picture says that understand this. So bias variance. So we have to understand the bias. What's the bias? So the basic measurement of bias is the model's true prediction minus y hat. This is the basic idea. This is bias. Okay. And variance is how much? So this is the average of this. In mathematical terms, expectation and standard deviation of this. In its, let's say, or maybe variance of this, standard deviation square of this. But you know variance, so variance is not a, so essentially variance. And you can actually also measure variance mathematically. So the idea to measure it is, so whole idea to measure bias is that if this is the definition of bias, if I pick up a random new data point x comma y, x star comma y star, we do not know x star, and we use the f x given theta, this is the already predicted one, x star, so we will get the y star hat. So the question is that, so if we get, so we have x star y hat star as a predicted and y star as the original. So the question is that, the question is, therefore there are two questions. One is how, so since this is a random, it's, remember it's random, so it can actually vary also. The, so the y star minus y star hat can vary, right? Can vary. And so since it can vary, we can ask two questions. It's a random number, random variable actually. So random variable. Since it can vary, we can ask two questions. One question is, on average, how it's behaving. So expected value of it. And what is the variability? Okay. So this is called bias. This is called bias. And yeah, so this is called bias. Did you understand? All of you? Can you say yes or no?
Yeah.
Yes.
Yes.
Okay. So the, yes. So what we're interested in, we are interested in this quantity, loss. So expected loss, that is how much this is different from this quantity. So it's loss, right? MSE, let's say, mean square error, square of the difference. You can show mathematics. So this is what our interest is. So this will tell you that how this random loss is. So this new loss, expected loss, you can show that this is nothing but this bias square plus this variance. Mathematically show that. We will not go into that. So this random loss is nothing but this bias square plus variance. Now, the beautiful part is if you increase the bias, as you can see, if you increase the bias, so in this case, you can see it's anomalous, but actually it's decreasing the bias actually. I mean, it is fitting all the points really well. Do you see the point? So here you can say high bias. So we can say bias high, variance low. Sorry. Yeah, bias high, variance low. Here you can say bias really low, variance really high. And here it's optimum. So you can see the whole basic idea is that if you increase bias, the variance will decrease and vice versa. So this is an optimum value. Somewhere optimum. Does it make sense, guys? All of you? Somewhere this is optimum. Right? All good? Anushka and Arav?
Yes.
Somewhere this is optimum. So question is that how to find that optimum? The question is that. How to find that optimum? This is a very important question. Otherwise, what will happen? So, okay, how to find that optimum? In deep learning, let's say. And also, how to find the optimum for a new data. Understand this, for a new data. Okay, this is very important. So two core idea. We take a random new data. And how to find the optimum. This is very, very important to understand. Okay. So you want to find the optimum spot. So you want to find the optimum spot, the model complexity. Why we are calling model complexity? So this is error, okay? This is error. So you can see as model complexity is increasing, as the model complexity is increasing, you can see model complexity increases. The bias becomes low, bias square, and the variance is become high. So somewhere when you add them together because of this theorem, somewhere there is an optimum. And that's optimum what we want to find. Golden spot. So for a new data, how to find the optimum? That's the question. So for the new data purpose, we have built this training test framework. Train, validation, and test framework. And for the optimum, it's actually both. For both, we have different ways, like different training strategies. Which we are for deep learning. So this new data, this is for mostly new data, getting the idea of the new data. So because we want to find for a random new data, that's what we want to find on average. All of you got it? Any questions?
No.
Super. For a new data, how to find this? Okay, all great. So let's first go into this training test validation framework. So first, a subset of this is train test framework. So what is a train test framework? Let me pull up a picture again. Okay. So this is the basic idea. So train test framework says that you have a data. So you train on past data and test on the test data. Test your results on the test data. Okay. Test result on the test data. So for example, you can train on this and find the best parameters. So you divide the data into two, train on one, and test on final data. Okay, that is the best way out. Often, so the basic idea is that take a model, use train data, and get result on test data. Right? Now, often, so understand what we want to understand. We want to understand the ideal performance of a model on a new data set. So if we have one model, this is good. This is perfect for one model. Good for one model. Now, if I ask you a question that what if there are two models, different models out here, like this, three different models? So this is the whole idea. What if you have three different models? So understand this. So often what you should think like test data is that test data is something. Test data is something. So understand this. So the best way to understand this is like this. You are a company. You train AI models. Okay. And there is a client, let's say. Or let's say there's a hospital. Or any other client. And they give you data. And the problem statement. That this is what you want to predict. So what they want to see is that, so they give you data, but they will have some, so they want to test on their, because they will not give you the data on which they want to test, right? Because then you have the data. So there is some test data here. So proprietary data. Always. So you can think of this like test data set. That is only when you, so what you will give them a single best model. F hat, F theta hat. Best model. That you know that it is good for their data. Understand this? So because you will not have access to this data point. So this is the best model that you know. So the question is that they have given you, let's say, whatever data for training. So now you have training, like whatever, you have training data, or you have data from them, companies data or hospital data. So the question is that how do you get, so you have so many models, you have so many models. How do you get not available? And let's say they told you that, okay, I need 90% accuracy for your model, otherwise I will not continue the business with you. So they want to test how good your model is, right? So how do you get the best model that you have? So that's the question. Did you understand the problem statement, guys? So that is the birth of validation data. So that's where the validation data comes in. Okay, so what is validation data? So this is, you can say this is for, let's crop it. So this is with them. Not available to AI company. So what you do is that you create a different unknown data. So just like the previous test for one model, you create a different unknown data. Do you understand? Create a different unknown data. Like, so whatever data I give, you divide your training plus validation. Let's say 80-20 split. Because you have so many models to work on, right? You have so many models to work on that you want to know that what is the validation accuracy. So what is it? So your hypothesis is, which is kind of true, that if a model performs well on validation data, then it will with high chance perform well on unseen locked test data that you will never see. You will only see the test data when you give away, like, so you make your model, you have no other choice, you go to the company, the hospital, and then you see your model working on that data, otherwise you will never have it. So you must give a really good model, trained model. So what we do, we divide the data they give, into two halves: training and validation. Okay, training and validation. So the basic hypothesis is this, and which is, it is mathematically true, because if you think that this, so let's call it TR, V, and TE, this three data set, and it's mathematically true that since both V and E are taken at random, these are random splits. So both have the same distribution. So both have, so ideally V is distributed same as T, same distribution. So on average, it should work well. On average. So this is mathematically proven. Unless there is like a different data shift. So mathematically, if so there is important, so data shift or domain shift. So to reminder, you have a data set. So you have a trained data set and a test data set. So the test data set is with, it's called unseen. And this is only what you see. And this data set is divided into two halves. Training. Yes, I know it's train, but this is so a validation. Let's say 80-20, just example. So let's call it TR, V, A, and TE. So if distribution of TR validation, because these are all random variables, is same as this distribution, then this is then all right. But ideally, but this TRV, this will always be same distribution because they are from the same data set, is not as test, then it's called domain shift. For example, you take an image from one company's MRI machine and another image from another company's MRI machine. So they may have some different ways and issues. Okay. So you have to always look at this by inspection. So that's why it's very important to inspect. Very important to inspect. For example, in my own research, we are working with, so we got a trained data on a histopathology data. We work with a certain mouse, a cohort of mouse, and we trained a model. It's coming out to be 93-94% accuracy on validation. But when we are actually testing on a different cohort, it turns out to be 90, instead of 93, 94, we are getting 89. And then we looked on the dataset, test dataset, and we saw that the second cohort of the mouse, the test dataset, is a mouse cohort which has more, it's more diseased in some way. So that's why it was not, it's not proper. So this is very important, guys. This is super important. But again, this is the best you can do. You can only do based on what you have. So this is also not just your fault. It's both the data provider's fault. So your goal is to have a scientific way to make sure you give the training data into two halves. And then, so once you get that, okay, returning back. Returning back. So you divide training test. So select, you have, let's say, model 1, 2, k models. So fix their performance on fix performance. So okay, not fix performance. Look at performance, check performance on validation data. Select the one with the best result. And then give it to the hospital for test data result. And then they write it in their paper or journal, whatever. But the whole idea of validation is nothing but you can think of it as a pseudo test, because you don't have actual test. So you're assuming that this is the same distribution as text, right? This is very important. All of you good here, guys? Any questions?
No.
This is very, very important. So if you don't follow this, then you are not doing it scientifically. So this is this process should be done very carefully. There should be no data leak from one place to another. So again, so we have a different test data. We have a training data, and the training data is divided into validation and train. So you feed the model here, validate on this, and do it for multiple models, select the best model, and then ship it and get it tested. Simple. Okay. So therefore, the whole idea is on validation data. So this is where you are testing. But again, you are assuming that the validation and test data are similarly distributed. Otherwise, it will not work. Okay. Now, here there is another question. So you want the model to be robust, right? You want the model to be robust. You want the model to be robust, right? So you can say that, so model, the selected model, the best model. So what can happen is that if you just do this by luck, and it actually happens more often than you think, like 20% time. So you're randomly selecting 20% of data. That means you have a 20% chance. Like if you think it carefully, this validation data set can be actually good, can be actually easily predictable, like easy to predict. So and that's a 20% chance. It's like 20% chance of having that. That's a large amount. It's not zero. So, but the other rest of the data is not so easy to easy. So for example, let's say you have something like this. So all these are red, and you have a green of this too. Okay, so this is the model. This is the data set. Okay, this is x comma x1 comma x2, the two features, and label 1 is red and label 2 is green. Okay, so now if you take a random, this is the entire data set, entire. If you take a random test data set, random validation data set, training and validation, it can come out to be something like this. So the validation can come out to be, so let's copy this. So the validation can come out to be something like this. So this is two different validation, let's say. Okay, let's copy the entire thing. So two different validations, let's say. One is easy. Let's say we remove this. Like this. And another is like this. You can see both are two different functions altogether. If this is easier to predict, but this is not easier to predict because you need a circular boundary here, but you can do it for the here. So you can need the easier boundary here, but here you need an intricate boundary, right? So this is a harder validation, and this is a easier val. Does it make sense? Right? So let's say the function has learned this, but this is not the ideal. The ideal boundary is what? The ideal boundary is this. This is the ideal, so it's very close to this. But what if you have an easier val here? So the question is how to deal with this. So what we do is something called cross validation. So it's very simple, it's very intuitive. So let me pull up that. So solution, what is the solution? Cross validation. So what is cross validation? Cross validation is this. Okay, cross validation is this. So we have the older entire data. So this part is with no, it's unseen. This is what we are seeing, and then we are dividing this training dataset into this. So that you can see this validation is fold 1, fold 2, fold 3, fold 4 is all over the entire training dataset. So what we are doing is that we are training on the rest and testing on this, training on the rest and testing on this, or validating on this. Test is not right, validating on that. And for all the models. So what does this give? Let's say one model is good and other model is bad. So understand, when we say good or bad, it's terms of expectation of. So we measure good or bad. So okay, measuring good or bad. So measuring good or bad is not just on bias or variance. The measuring good or bad is on loss. Why? Because that's, so what is the idea? We want to measure expectation of y star hat minus y star whole square, the average. So what is a good approximate of that? 1 by n summation of 1 by what is yi hat star yi hat val minus yi val whole square. This is the approximation, right? It's a very good approximation, right? Because that's the best you know. And so this is average loss. Average loss. because this contains both bias square and variance. Do you see the point? Both bias square and variance summation in this contains in that. So we are not just taking a bias or variance, we are taking both in this, right? So this is the very important idea. This is very statistically relevant. If you want to calculate average of a quantity, just or expected value of a quantity, you take the average of that, and that's what we are doing over unknown data set. And yeah, that's what we are doing. Okay, perfect. So understand that if, so let's say we have fold 1, so this is, let's call it loss. So let's say fold 1, fold 2, 3, 4, 5. This is called 5-fold cross validation. There can be multi, if it's 10-fold, it will be divided into, so in 5-fold it's 1 out of 5, so it's 20%, so 20-80 split. If it's a 10-fold cross validation, it's a 5-fold, because you're dividing the 20% into 5 parts. But if it's a 10-fold, it will be 1 out of 10, that is 10%, 10-90 split. So usually we do 3-fold, 5-fold, or 10-fold. But yeah, there's a detailed study on that. But the basic idea is it, that you have fold 1, fold 2, fold 3, fold 4. Let's say if it's easy, if this is easy, this will be really low. If this is medium, this will be, this is low, this is okay. But if this is hard, the loss will be a bit high. So what will happen is that this will become high. Okay. Also, often you can check the, because you will have 5 of them, right? You will have 5 such losses. So let's call it loss 1, loss 2, loss 3, loss 4, loss 5. Yes, the average of it is a good good measure of the average, the this. But interestingly, the robustness, how robust it is, because robustness is a definition of your performance over different data points. Robustness, how robust? So robustness definition can be as is the variance of y hat square minus y star whole square, the variance of that. So this is the performance, or how performing it is, how loss performing it is. But the variance of performance tells you that how, is it like it is only happening for good, or just it's so how much robust it is. So this can be approximated by, so you have got these 5 numbers, so it's 1 by n, so it's variance of, you can say it's approximated by variance of this L1, L2, Ln, L5. That means it varies, how it varies over this folds. Okay, so if it's one is a good fold, one is a bad fold, it'll average it out. So that you can think, so how varied it is. That also tells you how robust it is. How this is the model learning robust. Makes sense, guys? This is the very important points. Did you understand, Anushka and Vivan? So you have a training and test. I said the training is divided into train and val. If you want to compare model, now if so, ideally we just do this, just performance. When you have robustness to compare, let's say you have more statistical tests out there. But a good initial way is just performance. Just average those over all the folds. Okay, over all the folds, 1 by n summation. Like just average over all the folds. Anything else? Yes, this is it. So this is the basic idea of how to learn. This is whatever I have discussed, it's for any machine learning, not just neural network. The trick of neural network comes in when on how how neural networks happen. So, so neural networks happen like this. DNN. So you have a model. So what you do, there is an epoch. So for epoch in, let's say, number of epochs, for epochs in this, what you do is that every single time, so I'm skipping something which I will come back later. So what you do is that you have an X. Okay. So this is the input. You have a Y hat, which is function. And then you calculate the loss, Y hat comma Y. This is the prediction. This is input. This is loss. And we will come to this again later tomorrow. This is next you do loss dot backward. That is back propagation. So once you do loss dot backward, when back propagation happens, what happens is that the gradients are stored, are updated. Then, so you have, let's say, an optimizer in the sense, optimizer is how you do the, so that's a gradient descent. Like how you optimize. So what you do is that you now, because the gradients are up, the optimizer doesn't happen because gradients mean that del L, del theta i's are calculated. But it doesn't mean that your thetas are updated, the parameters are itself updated. It doesn't mean that. So what happens is that when you do optim.step, if you remember, then the thetas are updated. The parameters are updated. And then you do optim dot zero grad, if I'm correct. Essentially, or maybe, yeah, the optim of zero. Essentially, what you do is that you remove gradients for the next step. Let me just check if it's optim dot underscore zero grad. Oh, yeah. Yes. So the gradients are reset because you have updated. So this is a basic idea. And then, yeah, this is a basic idea. So then this happens for epoch. So when you run this for long, so since deep DNNs are universal approximators. Universal approximators. What happens is that since they're universal approximators, as you train, so this is the epoch, and this is the loss. So as you train, since they're universal approximators, training loss, because it's learning the best possible function possible. So training loss converges to zero. In most of my project, if I run for long, the training loss turns out to be zero. Most of them, because it gets to learn it. So then the question is that how to measure val. So what you do is that after this step, also measure So measure after each epoch. Measure train loss, average, and val loss. You will see that after a certain time the val loss decreases, but after a certain time it will increase. So this is val loss because it is going from the domain of learning. So this is underfitting. This is the domain of underfitting, and this is the domain of overfit. This is the optimum point. So this is where you stop training. Now this is different for, so this is understand, this is val loss, yes. So this is very different than other models, because this is, so you can think of it like at every step, the mental model is that at every step a new function is learned, because it's a universal function approximator. Every step a new function is learned, if you remember this. So they are different functions, right? So you can think of it like every step new functions are learned. So this is called early stopping. So this is very specifically for deep neural networks. You stop early. How you measure after every epoch, you measure both training and validation loss, and you stop where the validation loss started to increase. Does it make sense, guys? They're very, very fundamental and important, guys. Make sense?
Yes, sir.
So often people do one important thing when they have a large amount of data. In case of large amount of data, because okay, let's not go into there. Yeah, training DNA, perfect. This is super important. I'm telling you, this is super important. So there are other methods taken. So let me see if I'm covering everything. Cross validation, bias instead of yes. So final technique that is done is regularization. So what is regularization? Regularization is, so okay, understand this loss function is a parameter of theta, right? So what happens is that you find theta such that L theta is lowest. That's what you found. But in deep learning, the loss function is something like this. Like this. This is the loss function. It's very concave. So it's very hard to learn. So you're using gradient descent, right? You're getting gradient descent, and often people can. So ideally, it's this, right? This is the best point. So what we want often is to regularize it, to make it smooth. How do we do that? We add terms like this. We want theta square to be close, like we want one example is sparsity. There are many different ways to do it. There are many different ways. Sparsity, where we want, we deliberately make certain thetas 0. Why? Because not all, like if let's say y is equal to 5.1 x1 plus 3.2 x2 minus 4.1 x3 plus 0.01 x, let's say 0.11 x1 x4 plus 0.10 x5, you can see these are not important. So instead of saving this, we make it so. Probably these are the reasons why there are so much crookedness. So what we want to make them close towards 0 and increase the weights here. So what happens is that it kind of smoothens it and we get something like this. And now it's easier to learn because it can slowly move it up here. So this is the use of regularization. So what we do, this is something done by something called weight decay. So weight decay is nothing but adding a loss term. So this is the usual loss term, whatever the loss term is. So loss term is this usual L theta plus some modulus theta to the power some k. So that means you're minimizing both this and this. So essentially, when you add this two elements, that means you both want this to be 0 and this to be 0, right? And this is called weight decay. How much you want that weight on? This is very important. How much weight you're giving to the fact that you want theta to be close towards you. Make sense, guys? All of you? So what essentially the goal is, it makes the loss function smoother. Loss smoother, easier to predict, easier to minimize. Because it's hard, because we are doing gradient descent step by step. Step by step optimization, hard here. Easy. Make sense, guys? All of you? Very important stuff again. Regularizations. Okay? V1. So these are practical training methodologies for deep neural network learning process. So you can name it training deep neural networks. Okay, this is a fundamental. So we have learned training, validation, test framework. First, we have learned this framework. This is just for one model. So another part is hyperparameter tuning. So there may the other kind of different other kinds of regularizations, so something like dropout and stuff, but I'm not going to there. The whole idea of regularizations is to make the model learning smoother so that it's easier to learn and navigate. Okay, the final part, the second final part is hyperparameter tuning. So the thing is, how do you tune that? There are many different. So what is hyperparameter? So you know parameter, right? So this is a parameter. F of theta, this is a parameter. And when you are minimizing this, we get better theta. But hyperparameter is not inside. So parameters that are not part of loss function. For example, number of layers. That's a hyperparameter, right? Then this weight decay. How much weight to put on this? There are many others. Okay. Number of layers is one of them. Number of layers, number of neurons in a layer. So the main question is that what do we do? How do you find the best? How do you find the best hyperparameter? It's very simple. So a hyperparameter is what? A different model. So treat it. Every hyperparameter is a different model. Understand? Every hyperparameter is actually a different model. Model altogether. Not just a model, yes, different model altogether. Often not just a model, like you can see that, for example, model or algorithm, you can say algorithm. Why I'm saying this is because just as a model, for example, you can take the same model, but you can have different loss functions too. One with, so you can have loss 1, loss 2, but yeah, you can say diffs, yeah, different model. So you can have loss theta, the same loss, sorry, different loss, but here you have nothing, but here you have lambda plus, let's say, weight decay. Okay, you have weight decay. So what will happen is that the same function but with different parameters, but essentially it leads to a different model only. That's true, different model only, but again it's dependent on different hyperparameters. So how do you find that? So the framework is same. Select the best model on the validation dataset. That framework is same. Select the best val model. That is same, but how do you do it? How do you find it? How do you find it? You find it by different methods. One method is that you select, but how to find best lambda is select a range of values. Let's say 0.01, 0.05, 0.1, 0.15, 0.11, 0.15, let's say range, and select range, and everyone will do different training. So train on training, select lambda for which we get best val result. You see the point, guys? How to get the best lambda? Select the one which get the best val result, right? That's the whole idea. So essentially we treat say every hyperparameter, but here in the previous one, the changing theta changes the hyperparameter actually. Okay, but here it was happening automatically with epoch, but here it's not happening automatically with epoch. It's happening, you have to make it. So you have to have a for loop here and train it every single time and get the best one. That's one way. There are many different ways. All of you got it, guys? It's a discrete optimization. These are training secrets and techniques. Okay. I think this is all about it. Hyperparametric regularization, why it's important, training, how to train DNN. Uh, yes. The final thing now comes is this. That what happens. So let's understand this carefully. Okay. So let's see what happens first. So ideally, you have this raw data, you organize the files, then do some pre-processing, and all these things I will be coming next year. Okay. So we build something called dataset class in PyTorch. So I'll be doing all these things with you again. But I'm telling you one important, that is this one. Why do we need to divide in batches? This is the most important aspect. Why do we need to divide in terms of batches? Okay. This is very, very important. We have the train test file set up. That is also true. But this is the most important. What is batch here? Why do we need to do batch? And that's where we come to something called the final part is stochastic gradient descent. You can see after selecting the batches, we gave the model, the y hat, the loss, the gradients update, the get theta hat, the updated parameters, and get the y hat. But why batches? So this is where it lies in stochastic gradient descent. Why batches of data? The reason of why batches is this. So often this large, so when you train it, if you remember gradient, understand that. So for gradient, so revise gradient descent. So loss theta is nothing but 1 by n. Each individual loss theta. And then we have calculate the derivative of loss with respect to theta. Okay. And what we use it for? We have theta n or theta k is equal to theta k minus 1 minus eta times at theta is equal to theta. This is gradient descent. But understand there's a bottleneck here. Let's say n is 1 million data points. This will take a huge time to compute. A huge time to compute. So we do it in this way. So it's called stochastic gradient descent. So what we do is that we divide this entire data set. Data set into random. So this is random 1, random 2, or RB1, RB2, RB dot dot dot, RB let's say L minus 1 and RBL. So where RBI is nothing but random batch. A random batch, ith random batch. Such that, yeah, which is a subset of the entire training. Understand that? Training dataset. So what we do is that we create this first, and what happens is that in each epoch, so we, instead of this 1 by n, so we only consider the loss 1 by this RB, amount of RBI. So we do it batch wise instead of. So essentially so we have epoch, instead of epoch we have each batch, and each batch we do the optimization instead of the entire epoch. Instead of epoch and optimize. So what happens is that when we do this, the main question is that does it lead to, like, does it work? Because we are reducing the data set, so is the loss converging to the optimum minima? So batch of, so let me pull up a picture for you. Yes. So this is called mini batch stochastic gradient descent. When RB, so each batch size is 1, it's called stochastic gradient descent. It's called mini batch. So when each batch size is 1, it's called stochastic gradient descent. Yeah, it's called stochastic gradient descent. So you can see, let's copy an image. You can see that for batch gradient descent, it was smoother. For stochastic gradient, since it's one, it was very 1 by 1, it was like this. But you observe that the basic idea is on average, it's go to the same region, but there's error, random error. So what the basic idea is that we reduced batch. So if you reduce batch, increase epoch. So therefore, on average, it will go to that same point over time. So then mini batch, you can see it's a bit smoother because we have increased the number of data set, but less smoother than this. Make sense, guys? Yes or no? Did you understand? So what is happening here is, we will talk about this later, but every training data is divided into this B batches. And for each batch, the training happens. And when all the batches, so each epoch is nothing but training over the entire data set, but we cannot do it with the entire data set. So what we do is that we do it over each batch. So entire data set is divided into this B batches of sub data set. And on each of those B batches, the model is updated. Each of those B batches, the model is updated. Okay. And when all the batches are done, then we say the epoch, one training epoch is updated. And then each batch, this B batches, and which consists of one epoch, this happens hundreds and thousands of times to get. And at every epoch, we also calculate the validation loss. And then we look at this diagram, and wherever it starts increasing, we stop. And that's what, at that stopping point, we have a certain theta parameter saved, and that theta parameter is the best parameter for us. Now you can try multiple different training models, you have different hyperparameter tuning, but the basic idea is same. Okay, so this is what it means to train our deep neural network, guys. I hope you enjoyed it. It's very beautiful, actually. It's very, very beautiful. Did you get it, guys? Any questions?
No, sir, no questions.
Did you understand entirely?
Yeah.
It's a fully practical aspect. Okay. So next day, we have discussed the algorithm. Next day, we will understand the algorithm a bit better by implementing it on a real data set. Okay. What are the structures of it? For example, you have a data loader structure, data loader, how to organize and how it happens. It's very simple. Let's say it'll be probably 200, 300 lines of code. So we will code it live. So we'll understand. But these ideas will be very important. These ideas will be very important to understand the entire thing. I also taught the theory that why we are looking at this, the fundamental theory. And this is very important to understand. So in the future, whenever you are training deep neural networks, just refer to these notes and you will be good enough. Okay. So that's all about it, guys. And I hope you enjoyed it. I will see you tomorrow. Bye bye.
See you tomorrow, sir. Bye bye.